Hello and welcome. The 2020 AP Chemistry exam is coming up in just over a week, and as a high school student taking it, I still have some room to improve. That's why I'm taking the 2017 free response questions as a practice of sorts, and I'm recording it in the hopes that maybe it's helpful to you as well. But in that vein, I must mention that I am probably going to get many of these questions wrong, so don't take my answers as the answers. At the end, however, I will go over the official College Board scoring guidelines and we'll see how many mistakes I made and what I did get right and wrong. So I have a scratch pad, the questions, and a timer. And with that, let me start the timer. We have 105 minutes, which is an hour and 45 minutes. And let's go. So I'll pull everything up, and here we are. You can see me scrolling. On the left here, I have a scratch pad, so I can write out my answers. All right, we have the periodic table in case we need it. We have the equation sheet in case we need it. And I've got a calculator next to me here. So let's do this. Carbon tetrachloride can be synthesized according to the reaction represented above. A chemist runs the reaction at a constant temperature of 120 degrees Celsius in a rigid 25-liter container. Chlorine gas is initially present in the container at a pressure of 0.40 atmospheres. Oh, by the way, I should be done with this question at about, when this 44 is at 22, because we're supposed to have 23 minutes, is the suggested time. 23 minutes over here. So I'll try to finish this question in 23 minutes. Okay, so how many moles of chlorine gas are in the container? Okay, we know the temperature, pressure, and volume, so this is going to be a PV equals nRT kind of question. So let's do this. 1AI. We know that PV equals nRT, and it just tells us, it just asks us exactly how many moles there are. So let's just jump right into this. This means N is going to equal PV over RT. So we know that the pressure is 0.4. I'm going to just type this into my calculator here to save time. The pressure is 0.40 atmospheres, 2 sig figs. The volume is 25.0 liters. R, in this case, is going to be 0.08206. That's on the equation sheet if you don't remember it. And the temperature is 120 Celsius. Important to remember to convert that to Kelvin. So 120 plus 273.15. That should do it. And that tells us that the initial amount of moles of chlorine gas that we have are 0.3, and then we're going to have 2 sig figs. So my calculator reads 0.30996. I'm just going to write 0.31. I was about to write atmospheres, but this should be moles. Okay, there we are for part I. Let's move on to II. We're pirates now. II. Okay, how many grams of carbon disulfide are needed to react completely with the Cl2? Okay, so we have a mole ratio of 3:1 here, which means that we're going to need 1/3 the moles of CS2. So we're going to need 1/3 the moles, which means that if I divide the number of moles for chlorine I have by 3, we're going to need 0.103 moles of CS2, because for each mole of CS2 we get rid of 3 moles of chlorine. Now it's just a question of what the grams of this is. So if we head over to the periodic table, we see that for sulfur, we get the atomic mass is 32.06, and I happen to know, so we multiply that by 2 because there are 2 sulfurs, plus carbon is 12.011. If I scroll back down here, oops, too far. This is going to correspond to 7.9 grams, because I have 2 sig figs again, and I only had, on my calculator, read 7.8659, but I'm just going to round that to 7.9. Bam. Okay, that's that. At 30 degrees is part B, and why don't I switch colors just for fun? Because it's important to have fun, even on an AP exam. At 30 degrees, the reaction is thermodynamically favorable, but no reaction is observed to occur. Very strange. However, at 120 degrees, the reaction occurs at an observable rate. Explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120 degrees. So, this is going to be asking us for a particle level interpretation. And I would say, given especially this activation energy graph that they're giving us below, that what we can write is something like each reaction will require a certain activation energy, and we're going to say that this activation energy at 30 degrees Celsius, not many of these particles have it. So at 30 degrees Celsius, very few particles have this required energy. And because they don't have this required energy, we're going to say, so the reaction does not observably proceed, even if maybe it's proceeding at an incredibly slow rate. It's not observably proceeding. Okay. And then at 120 degrees Celsius, most, I should say not each, but most particles have higher speed, so higher energy, and they more often surpass the activation energy. Ooh, that often is not spelled with two E's. Surpass the activation energy. It's interesting that on the 2020 exams, they're only asking 2 free response questions, and these topics like free energy and activation energy, I believe, may not be on them. Activation energy maybe, but Gibbs free energy is not necessarily going to be on it. Oh, so this is only part I. Let's become a pirate again. Aye. Okay, the graph below shows a distribution for the collision energies of reactant molecules at 120 degrees Celsius. Draw a second curve on the graph that shows the distribution for collision energies of reactant molecules at 30 degrees Celsius. Okay, so let me get my graph color. This is the fun part about doing this without printing it out. It means that I have to draw the original graph as well. So in the same gray, this is something like the graph that they showed. This is the activation energy. And now we're going to have to draw a graph for 30 degrees Celsius. And I'll draw this one in green so that we match up. I would say it's going to look something like this. Let me draw in a different color so it doesn't interact with my old text answer. The reason it's like this is it's essentially scrunching up the curve, and you can see that the percentage of particles that are going to be over this activation energy is far smaller. So this is going to be the 30 degrees Celsius, and this is going to be the 120 degrees Celsius graph of particle fraction collisions. Yeah, there we go. Okay, the distribution of collision energies. Perfect, yeah, this looks very solid. So let's scroll it down. We've got 13 more minutes for this question. Okay, let's switch colors again for part C. Part C says, sulfur chloride is a product of the reaction. In the box below, complete the Lewis electron dot diagram for sulfur chloride by drawing on all the electron pairs. Okay, let me again get us a little box here like they've got. And going to use this blue color. So we've got Cl, S, S, Cl. They've kindly told us that it's a linear structure. I'm going to draw the electron pairs in red. Each of these is going to need 8 eventually. And what we need to remember is that sulfur is the same as oxygen here. So it's going to have 4 of these. Well, I guess what we can do is we'll start with drawing in, say, is we just have these valence electrons everywhere, and then we're going to be able to remove some of them because some of these atoms are going to be almost overburdened with valence electrons. So each of these we can just draw as a bond. So we can draw these each as, those would actually be double bonds because they had 4 electrons in the middle. And obviously we have some overloading happening, so each of these sulfurs doesn't really need these valence electrons more. And now we can just say, okay, these chlorines don't need these valence electrons anymore either. And now we have a situation in which technically all of the atoms are quote-unquote happy with how many electrons they have. So now we just need to count up how many valence pairs they have and see if it matches up what we should have. So each of the chlorines should be adding 7 to this reaction, I believe. So that's 14. Why don't we do it this way? 7 plus 7, and then each of the sulfurs is going to be a 4 because it's the same as oxygen. So this is going to be 14 plus 8 is 20. And with this 20, we count up and we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This looks correct to me. I'll also say that on the last practice test I took, I completely botched the Lewis electron diagram. So this could be wrong. Yeah, could be wrong. But I'm going to roll with it for now. Oh, wow, we've got the serious part I and part II going on. Again, pirates. Aye. Okay. Now it says, what is the appropriate value of the ClSS bond angle that you drew? If the two are not equal, include both. Okay. Interesting. So, the ClSS in this diagram, this is always what is terrible. In this diagram, I drew it as if it were linear because there are no lone pairs here to push them aside. So in that case, this would be a 180 degree bond angle. I'm just gonna say that it's going to be this 180 degree bond angle because that's what we put in for the Lewis structure. But I am aware that if, for example, this became a single bond, so if this was just a single bond and we then got like an extra electron, bam, then this would be a different bond angle. In this case, because we had a lone pair here, that would make it into, what, a tetrahedral, so 109.5 arc cosine of negative 1/3 if you ever forget. But that doesn't make the valence electrons add up, as far as I know. So we're going to go with a 180 degree bond angle and maybe be wrong. But that's where the learning comes in. The learning comes in when you're wrong. Moving on to part D, because now, let's see, how much more of this do we actually have? We have, that's it for that question. So we should finish part D in what? We would have 7 minutes. So we got to finish part D in 7 minutes, then we'll be on track. That's cool. So carbon tetrachloride can also be produced by reacting the blah with the blah at 400 degrees Celsius, as represented by the equation below. So we've got this equation. And, oops. At the completion of the reaction, a chemist successfully separates the carbon tetrachloride from the hydrochloric acid gas by cooling the mixture to 70 degrees Celsius, at which temperature the carbon tetrachloride condenses while the hydrochloric acid remains in the gaseous state. We're not quite a pirate yet. We just have the one eye. Identify all types of intermolecular forces present in HCl liquid. Okay. So we're essentially going to be explaining why the HCl gas is not going to be, why the HCl gas has such high intermolecular forces that when you cool it down, it's going to, oh, interesting. Well, I'm just reading part B, and it's saying what can be inferred about the relative strengths of the intermolecular forces in this liquid versus that liquid. Okay, let's start here. All intermolecular forces, clearly we're going to have London forces. That is always the case, and they just change depending on how many electrons there are. So this is London forces. We're also going to have dipole-dipole, because this is going to be a polar molecule. Dipole-dipole. And finally, we're going to have hydrogen bonding, because this is actually just such a polar molecule. We have hydrogen along with chlorine. I do believe that'll make some hydrogen bonding for us. We got all three types right there. Now we can be a pirate. Aye, aye. Perfect. Very nice. What can be inferred about the relative strengths of the intermolecular forces in carbon tetrachloride liquid and hydrochloric acid liquid? Justify your answer in terms of the information above. In carbon tetrachloride, we're not going to have any hydrogen bonding. So I would say that HCl liquid has much higher intermolecular forces, which I'll abbreviate as IMFs, I believe that's okay, than carbon tetrachloride liquid, because this carbon tetrachloride, if you think about electronegativities, this is not going to have a very high polar bond, so is not very polar. And on the other hand, HCl is like the epitome of polar because it's got hydrogen bonding. And hydrogen bonding is the strongest kind of intermolecular force. So HCl has hydrogen bonding, which is the strongest covalent intermolecular force, because obviously ionic is still going to be just stronger. It's, yeah. So which is the strongest intermolecular force, yeah, in covalent compounds. Why not just add it to be extra correct? In covalent compounds. Good for us. We're done with what? 2-3 minutes to spare? Really wonderful. Let's scroll down to the second question. Okay, and at the same time, I'm going to scroll myself down as much as possible right here. And we've got it. Perfect. So we see, answer the following questions about isomers, fulminic acid, and isocyanic acid. So let's do this. Let's switch back to red and say question 2. Another possible Lewis electron dot diagram, or two possible diagrams for fulminic acid are shown, and yeah, so that's going to be HCNO, are shown below. Explain why the diagram on the left is a better representation for bonding in fulminic acid. Justify your choice based on formal charges. One thing to know about formal charges is that you typically are more stable when you have more formal charge on the more electronegative element. So we can say, why don't we have formal, so yes. Okay. So we can say a Lewis electron diagram. Actually, why don't we not do that? Why don't we go the route of saying in the left diagram, oxygen has, that is a very strange M. Oxygen has a formal charge we got to remember that when we have a formal charge, this line counts for -1. Each of these electrons counts for -2. So it's going to have a formal charge of -1. So the oxygen has a formal charge of -1, while in the right diagram, it has a formal charge of +1 because it has these 4 pairs. Oh, sorry, actually it's going to have a formal charge of 0. But then importantly, and the carbon will have -1. Okay, so what's wrong with this? Well, the carbon having a -1 goes against its electronegativity being lower than oxygen. So we know that configurations is a good word for this. So configurations are more stable when negative formal charges, there needs to be 1 in this case, so when negative formal charges go on the more electronegative element. The more electronegative element. So thus, the right diagram is less stable. So the left diagram is a better representation. Alrighty, that should do it. So by the way, we are 23 minutes into the test as of now, because I know we started at 45 and now we're at 22. So we finished a whole part of the second question before we even needed to technically be done with the first question, and now we should be done with this question, give or take, at the 1 hour mark. Okay, so let's keep going. Let's keep going. Here we are. So fulminic acid can convert between isocyanic acid according to the equation below. We have a reversible reaction. I was noticing that. All right. So it's just changing the position of that nitrogen and carbon, it seems. Using the Lewis dot diagrams of fulminic acid and isocyanic acid shown in the boxes above and the table of average bond enthalpies below, determine the value of the enthalpy change for the reaction to form this. Okay. I'm seeing that. All right. Cool. This is a great question. Great question. Let's do this in the remaining space with a different color, of course, because that's just more fun. Just more fun to do it in a new color. We're going to do an enthalpy of formation. So this change in enthalpy is going to be equal to the enthalpy created by the products, which I'll write here as change in enthalpy for the products, minus the change in enthalpy for the reactants. Okay. Let's find what this is equal to the for the products. And you'll notice, however, that we're only given bond enthalpies. So the way this works is you have to imagine that you're creating every single bond that is in the product and breaking every single bond that's in the reactant. The reason we subtract this is that breaking bonds takes energy. Imagine ripping two magnets apart. It takes energy. And forming bonds releases energy, right? Imagine letting two magnets snap together. There's a really ringing sound because they're releasing energy as those two magnets snap together. And that's a long way of saying that we need to add the bond energies for all the products and subtract the bond energies for all the reactants. So let's do this. We've got HN as a single, I'm looking at the isocyanic acid currently. We've got an HN single bond. That's over here for 391. I'll just keep track of the units all being kilojoules per mole. And we've got to add that to, now we have an NC double bond. NC double bond, I'm looking here, is 615. And now we've got finally a CO double bond again, and a CO double bond is going to be 745. Not a half bad time to wake up, 745. Here we're going to be subtracting HC single bond on the fulminic acid. It's going to be 413. We're going to also be getting rid of a CN triple bond. That's going to be 891. And finally, we're going to have this NO single bond. That's 201. It should be adding. I'm going to plug this into my calculator here. Give me a second. And I'm going to subtract 413 plus 891 plus 201. And I'm going to get a total value here of 246, and the units were what? Kilojoules per mole. And that's the change in enthalpy for the entire reaction. Yeah, I think that's pretty good. I'm just checking. We're finding this for HCNO forming HNCO, which is perfect because we added the energy that we got from the HNCO and we subtracted the energy from the HCNO. It's funny, they sound very similar, HCNO and HNCO, but we did it correctly with the subtracting. So we're breaking these bonds and forming these bonds, so good for us. Okay, as you can see here, I'm out of space now, so I'm going to be shifting over to the right and scrolling up to the top. All right. And yeah, here are our original answers for 1. I'm just going to come on over here, and we're going to continue right here. Why not? Okay, so let's get part C going. Part C. A student claims that the change in entropy for the reaction is close to 0. Explain why the student's claim is accurate. For this, we don't really have any information about the data, the numbers for the entropy, but what we can say is that, going back to the definition of entropy as the amount of possible arrangements, we're only switching 2 atoms here. We're not really changing anything about how many configurations these particles can get into. So if we say that entropy is defined as the amount of possible configurations for particles, the amount of possible configurations for particles, then, so we can say, I would say swapping the position of the C and the N doesn't actually change, so it doesn't change the phase. It still remains gas. If it changed the phase, it would be a big change in entropy. So it doesn't change the phase, nor does it affect possible configurations. Therefore, change in entropy is indeed going to be close to 0. And why don't I just write that out? Why not? Perfect. All right, we got 15 minutes for the rest of this question. Let's again switch colors because it's more fun that way. Which species, fulminic acid or isocyanic acid, is present in higher concentration at equilibrium at 298 Kelvin? Justify your answer in terms of thermodynamic favorability and the equilibrium constant. Alrighty. We are going to have, okay, I can see two possible things we're going to need to do, but first let's just write out some definitions. So this is Gibbs free energy is equal to the change in enthalpy minus temperature times the change in entropy. And we also have that this is equal to negative RT times natural log of K, the equilibrium constant. I'm not quite sure which form to use yet. If we consider the left expression, because entropy is close to 0, we can ignore that term, and then we're only considering the H, and clearly the H is positive, so yeah, the temperature is going to come into effect, I believe. Are we ever given the equilibrium constant, though? How can we use this if we're not given the equilibrium constant? I am just a bit confused. Are we given that the reaction proceeds? Okay, so I guess it's telling us actually that fulminic acid can convert to isocyanic acid. So we could say that, I'm not going to write clearly because I'm not exactly sure, but we can say that this here is less than 0, which means it's favorable, because we are told that HCNO gas here, this conversion does happen. That means it must be at least somewhat thermodynamically favorable. Okay, therefore, when we write this out, we have that negative RT ln of K is going to be less than 0. That's what this implies. And if we just rearrange, we have this. These two guys are positive, so they're positive, positive, divide them, it doesn't really matter. All we get is that ln of K is greater than 0, where the greater than sign comes from the negative and the less than sign. So for the sake of simplicity, let's just, well, here it's greater than 0. So example being ln of K equals 1. K, oh, that's a horrible example. Why don't we make ln of K equal 2? It's fine. Okay, that would mean that K is equal to E, but more specifically that K is greater than 1. So this is just your example, but more specifically, all this really implies is that K is greater than 1. And that's all we need to know. Because as soon as K is greater than 1, let me just box, that makes it seem like I'm boxing this answer. I'm going to get rid of this example here. The purpose was to show that K is going to be greater than 1 given these circumstances, given that we know that the reaction does proceed a little bit. So K greater than 1, recall here, we can write K as the concentration of HNCO gas over the concentration of HCNO, and that comes from this equation, product over the reactants. So this being greater than 1 implies that the concentration of HNCO is higher. So the concentration of HNCO is higher. Yeah, is higher. Let's write it. Yeah, let's write it like that. Okay, this might be completely incorrect, but I do think that we have used the correct justification. I would say use that form. It's less than 0, rearrange to find that k is less than 1. Those are the important steps. Okay, let's move right along. All right, the ammonium salt. Let's switch colors for part C. And we've got 9 minutes, 10 minutes. The ammonium salt of isocyanic acid is a product of the decomposition of urea represented below. So we've got this ammonium salt, I guess. Okay. Cool. A student studying the decomposition reaction runs the reaction at 90 degrees Celsius, and the student collects data on the concentration of urea as a function of time. The student proposes that the rate law is rate equals K times CONH2. And that would make sense if this is primarily a forward reaction, so a very high equilibrium constant. I'm just putting that out there as my guess. So let's justify this in terms of the data. And why did I write C? This is E. I can just fix that in hindsight. Well, I can't really. Did I write the other ones correctly? Yeah, I have C, D, and E. Okay, cool. So they propose that it's K times this. All right. Explain how the data support. Oh, they use the plural data. I hate them. Support the data, the student's proposed rate law. So we have, yeah. Technically, we should just say it's because it's similar to an e to the x in its curve here, but what we really need to show is that it's rate order 1, I suppose, or rather that if we consider the derivative difference, they don't use derivatives. I don't know how to do this in a way that they would like me to. So I'll just do it in my own way, which is to say that the concentration of CONH2 always decreases. This is going to be the definition of e to the x proportionally to its own value. According to the data. And this is exactly what the student's expression suggests. This is exactly what the student's equation, or what their rate law suggests. Cool. And specifically, if we get out our calculator here, we see that initially it's 0.100, right? And then if we take 0.707 and we divide it by 0.100, we get that the rate constant is 0.707. And if we just keep multiplying 0.707 times, so 0.1 times 0.707, then we get 0.0707, that's the next one. And we take that to the power of 2, so 0.1 times 0.707 squared, and we get 0.4998. Okay, Okay, that's the next one in the series. And then if we cube the 0.707, we get 0.3533. That's the next one in the series, right? So we're essentially just showing the student's rate law predicts the values, so it must be correct. So I'll just add that. Student's rate law predicts data, so it's correct. And I'll add an exactly because it is exact. So it is supported by the data, to say the least. Not just here. So it is supported by the data. Alright, that's more than enough time to spend on this part I. Let's become pirates. Ready? Aye aye. Using the proposed rate law in the student's results, determine the value of the rate constant k, include units with your answers. Alrighty. We already did that. It's going to be 0.707, but just for the sake of this, we're going to say oh, I see. Phooey, we found it for 5 hours, and now, oh gosh. Okay, we can just use their equation for this, because like this is the kind of thing that math just solves so easily, but we're going to use their equation for the sake of it. So here we have it. Their equation is the natural log of the concentration at time t. This is something I am confident I could rederive if I thought about it, but I feel like saving my mental energy. Okay, here's what we're looking for. So let's roll. Got 4 minutes, plenty of time. So rewriting this, the natural log of concentration at time t is going to be at time 30, why not, is going to be 0.0125 minus the natural log initially is 0.1000. It's going to be equal negative k times t is 30 hours. Remember, it's hours. So if we solve for the left-hand side, this is the natural log of 0.0125 minus natural log of 0.1000. Calculate that's negative 2 point something. Then we multiply that by negative 1 on the right, and we divide it by 30. We find that this implies that k equals 0.0693. And how many makes 3? 0.693. A classic, like 1 over e over 10 or something right there. Although I'm not positive. And then the units are going to be, this is going to be hours. These concentrations here are going to be, the concentrations are going to be in moles per liter. So this is going to be in, want the rate to cancel out. So, sorry, this CO concentration here is going to be in moles per liter. So I want this to be in seconds per moles per liter, I believe. So we cancel out this, and we get, we want it in inverse seconds, I believe. And we can just check this, but 1 over moles per liters per second, I believe. Let's check up here with the equation sheet if that makes sense. It tells us that I mean, a rate is in terms of moles per liter per second. Maybe I'll go over this again later, but I think for now let's keep that seconds up top. It makes more sense to me that we would have a rate in terms of seconds, like 10 seconds, for example. Unless, of course, the rate is supposed to be unitless. Yeah, okay. We're going to just have to move on. I'll skip the seconds. switch colors. Everyone loves switching colors. This is part F, last part. And just 1 minute to do it. The student learns the decomposition reaction was run in a solution of pH 13. Briefly describe an experiment, including the initial conditions you would change and the data you would gather, to determine whether the rate of the reaction depends on the concentration of OH-. Cool. This might take a bit longer than a minute, but we're fine. So, pH 13. Okay, let's actually scroll back up to get here. Oh, it's a pity we can't have them both on the screen. So I'll just write it down. CONH22 is going to go like this with NH4 plus and OCN minus. Oh, what a bad N. Okay. The question is whether it reacts, depends on the concentration of OH minus. So the experiment can be as follows. Oops. Initial conditions you would change. Okay. First, we measure, so as a control, we'll just, I guess as a control, we have the data given. So we have the data already given as a control. So all we really need to do is, so for our experiment, oh, not the number 4. So for our experiment, we're going to perhaps add some hydrochloric acid. What do we need to consider first? So we're going to add the CONH22 to an empty flask, and how does this work? And what we're going to do, was there a temperature involved? Right, so empty flask at 25 degrees Celsius, so no reaction will occur, so no reaction yet. And then we're going to have, we're going to add, why don't we say some, let's say add a measured amount. We don't really need to specify more than that. Add a measured amount of HCl to the flask, which is implied. And then now heat to 90 degrees Celsius and record the concentration of the new line. Record the concentration of the, oh, not the, no, the CONH22 over time to compare with the control. And we really need to start moving on here to the next question. We're already 3 minutes in. No issues yet, but we will get more behind as we go, so let's move on. Again, 23 minutes, so we should be done with this one at about the 37-minute mark. Of course, we've already used up a bit of our time, so it's not the end of the world if it takes us a tad longer. So question 3 says, at high temperatures, we have nitrogen and oxygen can react to produce nitrogen monoxide, as represented by the equation above. Write an expression for the equilibrium constant Kp for the forward reaction. Okay, for the forward reaction, Kp implies in terms of partial pressures. So these are all gases. We're going to include them all. We have the concentration, not the concentration, excuse me. We have the partial pressure of NO gas, remember that we square this because of that 2 coefficient, divided by the partial pressure of the N2 times the partial pressure of the O2. And it's as simple as that. This is part A. For part B, why don't I just continue in blue? We didn't get to use it enough. A student injects these two into a previously evacuated rigid vessel and raises the temperature to 2,000 degrees Celsius. Wow, very high. At this temperature, the initial partial pressures are 6.01 and 1.61, respectively. The system is allowed to reach equilibrium. The partial pressure of this, of NO, is 0.122. Calculate the value of Kp. I see. Okay. So, we have the initial partial pressures. This tells us, so the initial partial pressures of 6.01 atmospheres plus 1.61 atmospheres. This is going to be 7.62 atmospheres. Okay, this is going to be the total, all right? Never going to change. This is the total. That's how we're going to know this. This is going to be our anchor for this problem, is that we know the total amount of atmospheres that we should have at 2,000 degrees Celsius. Cool. Now we know that the partial pressure of NO gas is 0.122 atmospheres. What we got to remember is that every time we create a molecule of NO, every time we create 2 molecules of NO, we're using up a molecule of N2 and a molecule of O2. That's to say that whatever the partial pressure of this is, if we are to divide it by 2, then, oh, you know what, rather, this is better. This is the partial pressure here. That tells us that, hold up. I think it's, because it's an ideal gas, it's equivalent to think of moles and partial pressures, so we can just do it this way. We have 6.01 atmospheres and 1.61 atmospheres. I believe what we can do is say that whatever amount went in to create the nitrogen, let me just do some calculations. Oh, do I want to? No, I don't want to. So, do I have to? Just trying to think whether I need to do mole calculations here. I really don't think I should need to. I think what I need to say is this is subtracting x equals 2x. This is correct. However much we subtracted here, it's going to equal 2 times that. Perfect. That means that these are each going to be, this implies that x is what, like 0. That was a bad idea to do math on camera. I think that's correct, right? 0.122 over 2. Perfect. I just need an extra 0 in there. It's not actually perfect. So that means that going back to our original Kp expression, the NO we know is 0.122. Okay, so 0.122 squared divided by, okay, the partial pressure of the nitrogen is going to be 6.01 minus 0.061 times the partial pressure is going to be 1.61 minus the same of 0.061. Bam. Assuming my calculations are correct, a certain Kp value is going to equal 0.0016 with 3 sig figs, I guess. Oh shoot. Yeah, I'm fine. Okay. So let me go back to this in 6.2. There's our answer. Okay? Which tells us essentially that this is primarily going to actually not go through with the reaction. Oh no, we only have one more column. Can we make it work? We don't have that much space left. I'm gonna try to make this work by doing this in 2 columns. I'm doing this in 2 columns so that maybe we can have enough space to do the final few questions here. On the exam, this will be time you can spend solving the problems while I am having to deal with my columns. So good for you. Okay, we got to kind of book it here. We've got some serious amount of questions to be answering right now. So, part C. Nitrogen monoxide can undergo further reactions to produce acids, such as nitrous acid, a weak acid with Ka of low and pK of low. A student is asked to make a buffer solution of the blah blah blah. Oh, I'll mention that on the 2020 exam, these Ka questions are not going to happen. But hey, I'm supposed to be learning chemistry, ain't I? Not doing this AP test or teach to the test approach, so I'm going to be doing these questions anyway, even though I haven't learned and I won't learn about them. So, a student's asked to make, not quite a pirate, a student is asked to make this buffer solution with pH of 3.04 by using so much 0.100 molar and 0.100 molar of that. Explain why the addition of 0.100 molar of the NaOH and the 0.100 molar of HNO2 can result in a formation of a buffer solution at all. Okay? The explanation here is that we're essentially going to have some of this weak acid floating around. So this strong NaOH will want to take all of those hydrogens away, but it won't be able to. So what we're going to have is, with NaOH and HNO2, we'll have, I'm going to need to write smaller, so I'm going to do that starting like now. So we'll have some NaOH left over, and we'll also have some NO2 minus, and we'll have some, so this is the unreacted, this is the reacted, we'll have some HNO2 left over. We'll also have some of the reacted stuff here, which is going to be, I believe maybe NaNO2 and H2O getting formed. So the buffer comes from the NO2 minus, because the NO2 minus really, really wants to accept that proton. So the buffer, and it comes from this weak acid, so the buffer comes from the NO2 minus wanting to accept. Okay, maybe that's insufficient, but again, I haven't really learned about this, so I'm just going to skip it. The net ionic equation for the reaction that occurs when the student adds the NaOH to the HNO2. The net ionic is going to be that the I think it's going to be, if we have these guys here, maybe, oh, wait a minute, this first. Let's just go out on a limb. Na plus OH minus, and it's going to go, well, I think the OH minus is just going to form. So I think, okay, again, not really sure what's supposed to be going on here, because I technically have not learned this yet, which is, as always, no excuse for not knowing it. but I think that it's going to be, just as a guess, Na plus NO2 minus. Technically reversible, but really it's just going to go become NaNO2. That's a guess. So guess. Okay. A second student makes a buffer by dissolving la moles of la, which is more resistant to changes in pH when a strong acid or strong base is added. The buffer made by the second student or the buffer made by the first student? Okay, so I actually have to read the laws. Okay. When the strong acid or strong base by dissolving, which buffer is more resistant to change in pH when, okay. So the first one is made with HNO2. So they're both made with HNO2. Only difference is, the only real difference is the NaNO2 and using 1 molar of HNO2. Well, I gotta say it's gonna be the second student. So the second students will be more resistant because he or she more resistant. Again, kind of going off on some limbs here because they used 1.00 molar of the HNO2 aqueous, which is the weak acid, responsible for creating the buffer. I say responsible for creating the buffer when I don't really know what's going on with buffers except for a few basic things. But hey, we'll just write down the answer and hope it suffices, and then learn more later. Let's move right on. A new buffer is made using HNO2. Let's switch colors. This is part E. You know, we're pretty far through the question. A new buffer is made using HNO2 as one of the ingredients. A particulate representation of a small representative portion of the buffer solution is shown below. Cations and waters are not shown. Is the pH of the buffer represented in the diagram greater than, less than, or equal to 3.40? Okay. HNO2 and NO2 minus. So for each NO2 minus, so I guess HNO2 has this Ka thingamabobber. Oh, you know, that Ka probably came in to be useful, but again, we haven't really learned about Ka, so it's not going to be on the exam this year, so I'll learn about it at a different time, more at my leisure. So what we need to do is count up, say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these HNO2 molecules. How many NOs? We have 1, 2, 3, 4, 5 NO2 minuses. For each NO2 minus, that's basically saying that we dropped the hydrogen. So it's a 1-to-1 molar ratio with hydronium. That means that the hydronium percentage is going to be 1/3. So the concentration of this H plus is 1/3. And if we recall, the pH is going to be the negative log of this, negative log base 10 of 1/3, which is the same as the negative natural log negative natural log of 1/3 divided by the natural log of 10. Yay, log facts. That comes out to 0.477. In other words, way less than 3.4. Prefaced with either that or way more or equal. Who really knows? Not me. Okay, let's move on. Hey, we finished that question with a wee bit of time to spare. We have 4 short questions coming up. Each of them should be about 9 minutes long. So let's aim to be done with this one by the 30-minute mark, because that's actually a quarter of what we have left. We just had a little bit of extra time. We're doing great. So question 4. A student investigates various dyes using paper chromatography. Oh, chromatography! That's one of the things I completely haven't studied yet. Let's do this. A student has samples of 3 pure dyes labeled A, B, and C, with an unknown sample, and an unknown sample that contains one of the 3 dyes. The student prepares the chromatography chambers shown above on the left by putting a drop of each dye at the indicated position on the chromatography paper, a polar material, and standing the paper in a non-polar solvent. The developed chromatograms are shown above on the right. Okay. So there's a non-polar solvent in the chromatography chambers, and we're putting the dyes. There's an unknown sample. One of the 3. The origin. Right. Okay. I really don't know how this is supposed to work. I really don't. But the paper itself is polar, so the least polar one maybe should be the one that didn't go up the furthest. I'm going to say dye B. Dye B, because the dyes solvent, right, because the solvent is non-polar, so we ignore it, and the paper is polar, and dye B moved the least, as in it had the strongest polar, the least strong, excuse me, I'm mixing myself up here, the weakest dipole-dipole interaction. As we come back to grading this, we'll see whether my completely made-up answer has any merit. Let's keep going. Which dye is present in the unknown sample? Justify your answer. Again, I preface this by saying I do not know what dye chromatography is. But it can't be dye B because they started in the same place and didn't end up in the same place. So, can't be B because they started but did not end. In the same place. Cool. Can't be B. That leaves either A or C. notice that, oh, I see, they're all moving up some amount. Oh, so somehow it's like they're crawling up away from the nonpolar solvent. I'm starting to understand chromatography, maybe. Ha. Okay, great. So, I see, yeah, maybe they're not, obviously they're not pushing away from each other. Okay. It's also not really at the same level as A. So it must be the di-di interactions that maybe are pushing it down or up. That's critical, whether it's getting pushed down or up. Maybe it would be B is the least polar. That would mean it's not. The key is that if dyes A and C are attracting B, then the unknown is die A. You know what? Let's earn some points on other questions by saying, thus, the unknown is man's greatest fear. No, I'm kidding. Is die A. I think it can't be die. It's really a stretch for it to be die C when it didn't go at all as far out. So, you know, it's not a complete answer, but who cares? We have a 50% chance of being right, or 1/3 chance of being right. Okay, let's finish this question by 25 minutes left. Yeah, seems great. Let's switch to a new color for question 5. Oh no. Yeah, there we go. A student performs an experiment to determine the enthalpy of combustion to propanol, blah 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 blah, which combusts in oxygen according to the equation above. Okay. The student heats a sample of water by burning some of this blah 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 that is an alcohol burner in an alcohol burner as represented below. The alcohol burner uses a wick to draw liquid up into the flame. The mass of the blah 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 is combusted. Combusted is determined by weighing the alcohol burner before and after combustion. Okay, cool. That's enough of that voice. Maybe we will need this equation, so let's leave it up there for now. Calculate the magnitude of the heat energy in kilojoules absorbed by the water. Assume that the energy released from the combustion is completely transferred to the water. Cool. So, magnitude of heat energy, that's simply, we don't even need to know the weights yet. This is just going to be the mass times the specific heat times the change in temperature. We know this. It's literally given to us. The mass is 125.00 grams. The specific heat is 4.18 joules per gram degree Celsius. And the difference in temperatures is going to be, pull out the calculator briefly, 51.1 minus 22.0, 29.1 degrees Celsius. Stay in our new area. Let's multiply this all together. Times 4.18 times 125.00. In kilojoules, I'll divide this by 1,000. Thank you very much. This is going to heat the water by, and how many sig figs? 3 it looks to be 3, 15.2 kilojoules. Great. Great. Based on the experimental data, now let's move on to part B with a new color, because why not? Oh no, that's the color of our boundary. Can't do that. Let's do red. Yeah, red. Based on the experimental data, if 1 mole of the blah is combusted, how much heat in kilojoules is released? Oh, I see. I wasn't even looking at the top of the table. It does give us the mass of this that's combusted. So now we need to just figure out this is how much energy is released given this mass, so how many moles were there, and then we can work backwards for if 1 mole were combusted. So let's say that 0.55 grams of, what is this even? C3H7OH implies, now 0.55, I'm going to divide this by the atomic mass. So carbon is 12.011, multiply by that by 3, plus 1.008 is hydrogen, multiply that by 8, plus 15.999, multiply that by 1. Tells us that this many grams is equal to this many moles of the same compound. Cool. And 15.2 kilojoules were released by such a small amount of moles. Tells us that 1 mole of C3H7OH would release, and now we simply divide 15.2 by the amount of moles that were actually there to say it would release a whopping 1660. Oh, still only 2 sig figs. So I'm gonna have to say this in scientific notation. It's going to be 1.7 times 10 to the third. Rounding off my calculation a bit. Kilojoules. Yes. Okay. It says to report it with the correct number of sig figs, which I sincerely believe to be 2 because it only gives us 0.55 grams. Now we gotta scroll down. It turns out that this equation wasn't actually that useful to us, because we just had the experimental data. It's that simple. That simple. So, oh wow, we're already almost done with the question. Let's get ourselves a fancy new color. Part C. A second student performed the experiment using the same mass of water at the same initial temperature. Why don't I go scroll up a little bit? At the same mass of water at the same initial temperature. So again, 125 grams at 22 Celsius. However, the student uses an alcohol burner containing this reactant, but it's contaminated with water, which is miscible. And remember that miscible means that it can form a solution at any concentration. So for example, alcohol and water are miscible, which is why you can have a beer that has a 0.01% alcohol concentration, or you could have a really strong shot of vodka that might have a 50% alcohol concentration. I don't know alcohol, but I'm just making that up. Those numbers up. But miscible means that you can form solutions at any percent compositions. The difference in mass of the alcohol burner before and after the combustion in this experiment is also 0.55. Aha, but we're going to be evaporating water as well. With the final temperature of the water in the beaker heated by the alcohol burner in this experiment greater than, less than, or equal to the final temperature of the water in the beaker of the first student's experiment, just for answer. Less. It will be less than. Less. This is because the second student's burner contains water, we can say that it will lose mass to evaporated H2O in addition to the the combusted C3H7OH. So what I can say is, thus the 0.55 grams change is not all from C3H7 OH, which means that the released heat, because only the C3H7OH, not the evaporated water, means the released heat will be lower. So the water, second student's burner contains water, so we'll lose mass in addition to the combusted, thus it's not all from, so the release heat will be lower. I think that's a pretty good answer. Let's move it right along. We're at the bottom. 2 more questions. Can we do it? Can we do it in 2 questions? Let's see, we had question 4 and question 5, so I think in theory we'll have enough space for this all. But in theory always works in practice. In practice it doesn't. Let's do this. Let's get some new colors going on. Purple. So exciting. Answer the following questions about magnesium hydroxide. And we should be done with this one with about 15 minutes left at this rate, or 16 even. At 25 degrees Celsius, the value of the solubility product constant, KSP, for magnesium hydroxide is 1.8 times 10 to the negative 11th. That's to say it's pretty low. So the first question says, calculate the number of grams of magnesium hydroxide that is dissolved in a 100 milliliter saturated solution of this. So saturated solution tells us that we are as high as we can be. So this is telling us we're going to need to calculate the solubility in terms of grams per liter. The first way is we're going to need to find moles per liter solubility and convert. And we're going to remember that the solubility is this moles per liter. So we're going to want to find the moles of magnesium essentially per liter. We know this in terms of the concentration because the KSP, which equals 1.8 times 10 to the negative 11th, also equals, in this case, it's going to be the concentration of magnesium with the coefficient of 1 times the concentration of OH squared. There's a 2. Cool. Now, we know that for every magnesium, there are going to be 2 hydroxides. So if we write magnesium as X, we can write hydroxide as 2X. So 4X cubed. That tells us that we take 1.8 times 10 to the negative 11, just typing this into my calculator. Sorry about the delays. And we divide that by 4. And then we take a cube root of it. That tells us that the X, which is equal to the concentration of magnesium, equals 2 sig figs, 1.7 times 10 to the negative 4. This cubing operation is very important. You can't just square root it. You got to remember this 4 as well, which comes from the 2x. Cool. This is, recall, in moles of magnesium per liter. This is a concentration. Right? Yes. Moles per liter is the unit of concentration. So the first order of business is to turn this from moles per liter into grams per liter. It's kind by telling us the molar mass. So we simply multiply our result by 58.32 to find that the grams per liter, this is grams of magnesium per liter, and we got to multiply by the entire magnesium hydroxide, even if we're just looking now for grams of magnesium, but it's going to be 9.6284 blah. Okay, but we only actually have this many sig figs. I'm drawing a line there. Grams per liter. Cool, I guess we'd already written that. And finally, how many liters do we have? We only have 0.1 liters. So this implies that in 100 milliliters, we get the final answer. We just divide our final thing by 10. Oh, shoot. This is times 10 to the negative 3. Final answer is it's going to be 9.6. Again, only 2 sig figs at the end. 9.6 times 10 to the negative 4 grams. The critical point was the 4x cubed. That's important to remember. That's how we can work backwards from the KSP to the solubility, which is then just straightforward to get back to the amount of grams. All right, let's switch. This purple color sure is a bit dark, so let's get magenta. The energy required to separate the ions of magnesium hydroxide crystal lattice into individual magnesium 2+ and OH- ions, as represented by the table below, is known as the lattice energy. Indeed, that is. As shown in the table, the lattice energy of strontium hydroxide is less than, oh yes, a Coulomb's law, less than the lattice energy of magnesium hydroxide solid. Explain why in terms of periodic properties in Coulomb's law. Perfect. I love this question. So the answer is going to go something like, the radius of strontium is larger than the radius of magnesium because it has more electrons, so it's going to have a higher valence orbitals occupied, and Coulomb's law says that force is equivalent to the negative of the square of the radius, so the radius between the atoms in strontium hydroxide is greater, which means it has less force, so less energy. Bam, let's write that all down. So, oh no, I'm misspelling. Coulomb's law implies that, oh, and their charges are the same, so it doesn't matter, that greater distance between the molecules in a lattice makes for a lower energy. Cool. So strontium, and just in parentheses, strontium and magnesium have the same charge, so we ignore this. Next, oops, strontium has a larger atomic radius than magnesium. Oh, gotta stretch out my hand. It's getting sore. Radius than magnesium. I don't know why I wrote that whole word out. I should have just written Mg. And this is because it has electrons occupying, I guess we'll just get this, electrons occupying higher valence energy levels. Okay, so therefore, and it's kind of implied that the OH is going to be the same in both cases. So the strontium OH2 has a greater distance between lattice points. There might be a more concise way to write this. There's a greater distance between lattice points than does MgOH2. There we go. So Coulomb's law says it's lattice energy will be lower. Oops. As described above. Cool. That's all. Final question. Exciting times, right? Okay. A student wants to determine the concentration of hydrogen peroxide in a solution of hydrogen peroxide. The student can use one of two titrants, either dichromate ion or cobalt 2 ion. The balanced chemical equations for the two titration reactions are shown below. Let's scroll down and get ourselves some juicy space. I'm very happy I did this division on the last column here, otherwise I would not have enough space. So let's do it in a green. Yes, green is very fun. Okay. The balanced chemical equations for two titration reactions are shown below. All right. The half reactions and voltage values, this E, I don't actually know what E stands for, electrolysis or something, for systems related to the titrations above are given in the following table. Use the information to calculate the following. Oh, we're going to get to be pirates again very shortly. E for the reaction of the chromate, dichromate, and the cobalt. Cool. So they both have +2 charges. Okay. Okay. So one important thing to remember is that if we flip these half reactions around, that will make the voltages be negative. But if we multiply by 2, the voltage will not double because voltage is a measure per charge, so it doesn't get scaled when you multiply, only when you flip. Cool. So I'm going to write this down here just so we have more space. The reaction of this chromium. So let's look at the chromium equation. It looks like we have 3 hydrogen peroxides going in along with 1 dichromate. So where do we have the hydrogen peroxides going on? So the second half reaction that we're given talks about the hydrogen peroxide, and it tells us that we take 2 electrons and we create the water, and the water is what's going on in this equation. For the dichromate, we're creating water, so that tells us this is in the correct direction. How many times do we need this? 3 times. But like we said, that's not going to actually change the E value. So for this one, we're going to need 3 of this, but it's not going to change the E value. So I'm going to say the E total, and it's just telling us to calculate, not justify, so E total is going to be 1.77 volts from here. Now we need the dichromate reaction 1, and notice this is the third one. So the dichromate, oh, I see. Just a second, I'm looking at this bottom one here. I see, we need to do one more thing. So we have this, we're creating 6 waters here. We're creating 6 waters. We're also using up, oh, hold up. Yeah, I think what might be going on here is actually that, okay, I read this wrong. Get rid of this 1.77. The key is that we're going to get we're going to get 2 chromiums and 7 waters, all from the dichromate reaction. So all we actually care about here is the bottom reaction, which tells us that we're going to be converting the peroxide into the necessary H pluses and E's for the chromium reaction. Because look, we need 3 of these. 3 of the bottom reaction is going to give us 6 H pluses along with 8, makes 14. 2 times 3 is 6. 6, bam. All that tells me that we need -3 times this reaction. Remember, the 3 doesn't count, but the negative does. So we're going to get negative 0.70 volts from this reaction. Okay. That'll also produce the oxygens, the 3 oxygens we need. Now, we're going to use the chromium reaction just once, say 1.33 volts, because we're just taking it as is. And we're going to use our calculators to find negative 0.70 plus 1.33 comes out to 0.63 volts. There's our answer to the first question. Now we're pirate ready? Aye aye. Okay. Aye aye, matey. Now we do the same, but for cobalt. In here we've got 2 cobalt 2 pluses, and notice we've got cobalt 2 plus turning into cobalt 3 plus, so we're going to have to reverse this reaction right here. Okay. We're going to have to reverse this reaction. That tells me immediately that the E is going to be here, negative 1.84 volts. Because we're reversing this reaction to get CO2 plus turning into CO3 instead of the other way around. And we're going to need just 2 of those. Again, the 2 isn't going to affect the voltage, though. So 2 of these, and then what hydroxide are we going to need? We're going to need to use the second hydroxide equation. The second hydroxide equation turns the hydrogen peroxide into water. That's what we want. We just want it straight out of the box, going the direction given. That's 1.77 volts, volts, volts. I'm going to use my calculator just to be extra sure, but I'm pretty sure this is going to evaluate to negative 0.07. Yep. Cool. Part B. Stick to green, I like it as a finishing color. Actually, why not go magenta for a little bit more of that magenta fun. We haven't gotten enough chance to use it yet. Based on the calculated values of E, the student must choose the titrant, for which the titration reaction is thermodynamically favorable at 298 Kelvin. Which titrant should the student choose? Explain your reasoning. Well, if he chooses cobalt, he'll have a negative voltage, which means it will not be thermodynamically favorable. So he should be choosing the dichromate. So the student, oh, we gotta become pirates again. Excuse me. The student should choose the dichromate because it has a positive voltage which makes it thermodynamically favorable. Which makes it thermodynamically, such a long word, favorable. In first grade, I never would have known I would be writing words that are what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 letters long. My first grade self could not have imagined. So, okay, the student should choose the dichromate. Just to be clear, I'll underline that. Next. Hey, last time we're going to be a pirate this exam. Aye. Calculate the value of the change in entropy in kilojoules per mole reaction for the reaction between the chosen titrant and the thing. Cool. Going back up to our equation sheet, we can find a value, or rather an equation, for G. It's down here. G in terms of E. So G is going to be equal to negative NFE, where F, in case we don't know, is Faraday's constant, it seems. So when I say in case we don't know, I really mean because I don't know. So this is coulombs per mole of E minus. Let's do this. So the G value in E, perfect. Perfect. So if I'm not mistaken, all we need to do is say, oh, what's the N gonna be? Shoot. This comes from me having not studied this electric stuff. And it technically won't come up on the exam, but still. N is the number of moles. I don't really understand how we have a number of moles in this situation. How does one have moles when it does not tell you how many moles there are? This does not make sense to me. Per mole of reaction. Okay. We can say perhaps that the number of moles, will it cancel out with F? Because that has a moles in it, moles of E. You know, I'm going to go... Oh, of course. This is just kilojoules per mole of reaction. So perhaps... Oh, voltage? Huh. How does voltage going to be comparing to kilojoules? Very confusifying. Nonetheless, I think I'll just roll with maybe N being 1, because that'll give us moles per mole of reaction. I have no idea if this is how this is supposed to be done, but time doesn't really permit other ways. So -1 times 96,485 times 0.63. That's a number of joules. Divide by 1,000. Get the kilojoules. This tells us it is -60 kilojoules per mole of reaction, which is definitely thermodynamically favorable. Oh, did I get the correct number of sig figs? Yes, I did 2 sig figs. Oh no, 61, because it's actually 60.07. We got to round that to -61. All right. I think that's a wrap on all the questions there are on this exam. I know if I were to revisit the question, I think there's a highest chance of me getting an answer wrong on. It would be the die question. This is the end. But I don't really know how to do the die question, so maybe I will go back to the very first question I did before I was in the chemistry mode and see if I made any silly mistakes. Seems like a good thing to do. So did I make silly mistakes right up front? Often it's either at the start or the end. Okay. It said how many moles are in the container. It looks like I just calculated it with PV equals nRT, and I do believe myself. And then the grams of CS2, I also think that that looks very reasonable. So for I, we do have this certain activation energy, and at 30 degrees Celsius, very few particles have required energies. Okay, that I again agree with. Oh, the Lewis dot diagram. Again, I'm going to need to review these, but we've got 1 minute to see if we've made errors. Have I made errors? Most likely. So each of these chlorines, again, is corresponding to 7. Each of the sulfurs, or sorry, each of the chlorines is corresponding to, oh, shoot. Each of the chlorines is corresponding to 5. See, this is why I'm not really good at doing these things. What I'm going to say, what seems most probable to me, is this configuration, which would create a 109-degree bond angle. Let's rewrite this to be more clear. I don't know exactly why I feel like this is a better answer, but yeah, we're gonna roll with it. It just feels, maybe, I don't know what it feels actually. Oh shoot. Let's just pretend the exam hasn't ended. I need those double bonds to make things work. Okay. My timer's up, so I'm gonna stop that timer. And now what we're going to do is briefly go over the questions and just check whether I've gotten them correct. So let's do that. Got a tab over here with the scoring guidelines. Let's go over everything I did and see how well I did it. I think I'm going to use what color should I use for this grading? I'll use white, because I didn't use that very often. Okay, so first off, and going through the scoring guidelines is a great way to check your work and also to see what they're actually looking for. So we have 1 point earned for the correct answer with supporting work. Yes, we definitely earned this point here. Good for us. For part II, pirate, almost time, we get 1 point earned for using the correct mole ratio. Maybe implicit. Yes, in our case, I think it is implicit, and 1 point is earned for the mass of CS2, 7.9. I think we get both of those points because it is implicit that we're working with a 1-to-1 mass ratio. Otherwise, we wouldn't have been able to do the 3, or sorry, not the 1-to-1, the 3-to-1, because otherwise, you see how we just started with the 1.03. That makes it implied. Let's go over to part B right here, where we can say, at higher temperature, the particles have a greater average kinetic energy than at lower temperature. There are more collisions with sufficient energy to overcome the activation energy. Okay, so all we need is an appropriate explanation with a reference to molecular collisions. We said each will require a certain activation energy at 30 degrees Celsius. Very few particles have the required energy, so the reaction does not observably proceed. At 120 degrees particle, most particles have higher speed, so higher energy, and they more often surpass the activation energy. Shoot. Somehow, I did not use the word molecular collision. So this is not actually going to get the point. I think in my head, I had the exact right way of thinking about this. But what I should really do is say, instead of they, I should write this as molecular collisions. So molecular collisions more often surpass. And why can't I write collisions? Collisions. Yeah, unfortunately, I do not earn that point. Got to be harsh with yourself when you're grading. So 1 point is earned for part II for a curve that has a peak above and to the left of the given graph. So yes. 1 point is earned for a curve that is below the given curve in the region beyond the activation energy. I earned both of those points, luckily, to make up for a... Honestly, I understood it, so that's just, I would call it a silly mistake for the previous part, that I was not able to write it out correctly. Okay. And this is an example of me again needing to review these Lewis dot diagrams. What I was doing at the very end, I remember, was I was writing out a diagram that looked something like all these CLs and then the S, and then the S, and then the Cl. This is what I was going for, but I kept the double bonds and I didn't keep these guys. So I think what I need to do is count up correctly. The chlorines are 7s. Okay. The oxygens are 6s. Or why don't I leave that there? And so I need to think of in terms of total electrons. This is the correct, by the way. So in terms of total electrons, it's 7 plus 7 plus 6 plus 6 is 14 plus 12 is 24. And then when I count up, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Wait, what happened there? I have 8, that's 16, and then plus another 8 is 24. Funny. It's like I'm counting one extra electron for some reason. I don't really know why. Okay. Yeah, I'm going to revisit these Lewis guys. Clearly, something is off with how I'm thinking about them. Oh, no, nothing's wrong. 7 plus 7 plus 6 plus 6 is equal to 26. Aha! Aha! And then we get 8, 8, 8, 2, 26. Bam! So I need to not add up. It's like I'm subtracting. I was subtracting bad things from the oxygens. I just needed to consider all the electrons and then how they worked out. Luckily, coming back, I did end up changing the bond angle to be better. 109 degrees. So 1 point is earned for an acceptable angle that is consistent with the Lewis diagram. At least the Lewis diagram I gave, despite being wrong, is consistent with this. So I'm going to get 0 out of 1 points here, but 1 out of 1 points here. Okay, not bad. I mean, sorry. Bad, but not like that bad. Okay. Funny. 1 point is earned for both types of forces. I don't see... Isn't hydrogen bonding in effect here? I would think hydrogen bonding is in effect because it's got a hydrogen and a chlorine, but I mean, this is the kind of thing where an AP exam grader might give me the point, but being my harshest self, I think in good conscience I can't give myself the point. Just because I want to write exactly what they're looking for. So maybe they don't consider hydrogen bonding? I really don't know. Or maybe hydrogen bonding is only with fluorine? I'm pretty sure hydrogen bonding happens with chlorine. Anyway, so not really sure what's going on there, but hydrogen bonding shouldn't really be there somehow. Okay, so the intermolecular forces among the ClCl4 molecules must be stronger than those in the HCl molecules because this one condenses at a higher temperature than HCl. HCl has a much higher IMFs. I'm doing the opposite. Okay. Crazy. So I again earn no points here. If we go back to what this question was even asking, it said identify all types of intermolecular forces in HCl and then what can be inferred about the relative strengths. I was all gung-ho about saying hydrogen bonding therefore must be stronger, but you need to look at, I needed to look at the actual information. The information said that the CCl4 condensed while the HCl remained gaseous. So it condensing first meant that it had higher intermolecular forces. I should have known because it asked for justification in terms of the information above, not in terms of the information above, not in terms of the answer above. So, boo-hoo, but whatever. Counting out my points. I have 0 of 1, 0 of 2, 1 of 3, 1 of 4, 3 of 6, and then 3 of 7, and then 6 of 10. So for the first question, I got 6 out of 10, which is a pretty shabby score. I'm being harsh on myself. If a real AP exam grader was grading this, they might have finagled a way for me to get an 8, but I'm not going to expect any finagling. Oops. Okay. Let's move on to question 2. So this is the formal charge guy. So we can say in the diagram on the left, C atom has a formal charge of 0 and the O atom has a formal charge of -1. In the diagram on the right, the C atom has a formal charge of -1 and the O atom has a formal charge of 0. The diagram on the left is a better representation because it puts negative charge on the oxygen, which is more electronegative than carbon. So I need 1 point for a correct assignment of formal charges. In the left diagram, oxygen has a formal charge of -1. In the right, it has a formal charge of 0, and the carbon will have -1. Oh, I probably should have said that the carbon would have a formal charge of 0 in the left diagram. But you didn't really need to talk about the formal charge of the carbon on the left diagram, so... I mean, more stable and negative formal charges go on more electronegative elements. Therefore, the right is less stable. I don't know. To be honest, I think that I would earn both points here. So, even though I technically didn't write the formal charge of carbon on the left as 0, I don't think it matters in this case. I think. Okay. Now we have these bond enthalpies. Fun. So, oh shoot. Okay. So, I'm dumb. Because a broken bond corresponds to energy that is required to be put in, and a positive H means you need energy put in. So I should have taken the enthalpy of the reactants minus the enthalpy of the products. That is an inexcusable error, and it loses me the first point. And 1 point is earned for the correct determination of the change. It also loses me the second point, because it's an incorrect determination. I have it backwards. I should have known that because the products had higher than the reactants, it should have been exothermic, which means H should have been negative. So this is my learning for today. One of them is to remember that this being less than 0 means that it is exothermic. And same with the other way around. This is also an implication. They are both implications. Okay, cool. So, pains me. Process, correct. Small detail, wrong, lose all points. Okay, that's sad. Very sad, very sad. Must be more careful next time. Must be more careful. Let's go. Entropy is defined as the amount of possible configurations of particles. Swapping the position doesn't change the phase, nor does it affect the possible configuration, therefore it close to 0. The change from fulminic acid to isocyanic acid is a rearrangement of molecules, no change in the phase or number of molecules. So bam, we earn our point. Cool. Isocyanic acid will be present in a higher. So isocyanic, let's check which one that is. Yes, HNCO. So I'm correct there with a valid justification. The justification is that delta G is essentially equal to... Oh, I see. Shoot, this is getting back to it. And I should have figured this out the minute this happened. Because remember how I dismissed this equation as not going to be helpful? Because clearly I said the temperature has an effect because the enthalpy is positive and we need it to be thermodynamically favorable. No, passed from this self. No, it was the entropy that was negative and you that were being a dumb mistake maker. Not that we should call ourselves dumb, because growth mindset means that we can fix these things. But in all reality, that should have been the point at which I noticed that this was a problem. So since, I mean, somehow I got to it anyway. We figured out that K is greater than 0. And since this is negative, it is a higher concentration of product than reactant at equilibrium. So 1 point for correctly connecting thermodynamic favorability to the equilibrium constant K. Yes, I earned that point. I do have the correct choice. My justification is not valid, so I only earn 1 point. And again, I think I had the thought process exactly down, but I just needed to remember that enthalpy negative means it's releasing energy, and obviously it was releasing energy, so enthalpy needed to be negative. Slightly confusing things, but I think it's backwards that it isn't positive when it's exothermic, like you're releasing energy, but it's that it takes energy required to complete. Okay. Let's keep going now. Oops. I don't know what's going on with the scrolling here. So, from inspecting the data table or the graph, it is evident that a decomposition reaction has a constant half-life, which indicates the reaction is a first-order reaction. The concentration always decreases proportionally to its own value, according to the data. I should have said first-order reaction. So, okay, I definitely earned this point, but for the future, a faster way for myself to do this is to say something along the lines of what they're saying. So constant half-life, which this is where I really start to hate that AP doesn't have calculus built in and stuff, because it's so easy if you can just reference a little bit of derivative stuff, like proportional to its own derivative, therefore it's e to the x, therefore it's first order or whatever. But constant half-life implies first order. That's that. Using the proposed rate law and the student's results, determine the value of the rate constant. H minus. What in the world is H? Hours! Oh! Remember how I said this was 30 hours? Again, these are the kinds of things that I think I should just write out units and be extra careful about not making these kinds of silly mistakes. I said this was 30 hours. So the rate here, the K here, okay, the rate is in moles per liter. I don't need to have this inverse moles per liter. What I should have just said is that this 30 is dividing by the hours, so it's gonna be inverse hours. 0 of 1. Again, the right value, the wrong units. I think I do really need to think about this. I really need to think about this, especially so as a first order reaction, I could have used a simpler equation. Going through these problems is how I'm learning these, because with school letting out due to the COVID-19 crisis, we haven't gone over all of this. So this is essentially self-taught portions that we're going over right now. But I need to get the units straight, and messing it up one time on a practice exam is ultimately the way I want to mess it up. And then not on the next practice exam and not on the real exam. Okay, let's move on. The student learns the decomposition. Okay, so perform the experiment at a different concentration of OH minus and measure how the concentration of CONH22 change over time. Okay, as always, their descriptions for the experiments are so brief. All they really wanted was to have more OH minus, which, okay, sure. By adding a measured amount of HCl, we would change that. So it's just, they're saying just vary the concentration of OH minus and measure the concentration of this. So, I mean, yes, we get the point. We gave also way more detail. We gave an actual experiment you could do instead of just theoretically. Other variables such as temperature should be held constant. Constant, yes, but we do need to be at 90 degrees in order to have that control. So I think we're still getting it there. Okay. Oh, let's count up the points for question 2. So 1, 2, 3, 4. out of 6 so far. 4 out of 6. And then we get 6 out of 6 again. 6 out of 10, sorry. All right. Really not the performance that I'm looking for here. And it all, 100% of it, came down to my enthalpy mistake. So I need to be careful with how I do my enthalpy, and just keep that in mind, that enthalpy is probably going to trip me up if I'm not careful with it. And then hopefully I'll be fine. Yeah. So be careful with enthalpy. I'll write it to myself. I'll write it as, don't play with fire. Oh no, that's not how you spell with. With fire, aka watch your enthalpy. Yeah, watch your enthalpy, man. Cool. That's my message to myself. Watch your enthalpy. Okay, let's move on. There's plenty of time on question 2. Okay, we get our point for the correct Kp expression. Yep. So here, they made an ice table. I never really did those ice tables, so I just do it my own way, which is the same way, but just my own way. 1 point is earned for the correct equilibrium partial pressures of the reactions and products. Yes, I did that. I did that. I don't really know why this became a 2, but I assume they would accept that because it's obviously close. I don't know. I'm giving myself 2 points because aside from that, I think it might have been a rounding thing that I did. Yeah, I'd imagine that that'd be okay. All right, now we get to the 2-column era. NaOH will neutralize some of the HNO2 to produce NO2-. Ah, this is the buffer question that I didn't really know what I was talking about for. So the correct answer, this is a great learning opportunity for me, will be NaOH will neutralize some of the HNO2 to produce NO2-. The resulting solution contains a mixture of a weak acid and its conjugate base, which is a buffer solution. Okay. So what I need to remember is mixture of weak acid with conjugate base makes a buffer solution. This makes sense to me. Also, writing while speaking is hard, but this makes sense to me. Oh no. See, writing while speaking is hard. Of weak acid with conjugate base. This makes sense to me because either the weak acid or the conjugate base is going to be buffering your directions whenever you add acid or base. If you add base, the acid will buffer, and if you add acid, the base will buffer. Cool. So the ionic equation that we should have had, just not looking at the answer right now, it would have been, see, we have, it should have been that NO2-, I'm not looking at the answer, I'm just writing this out to see if I have it, forms a reversible reaction to make HNO2. Is that it? No. Oh, yes. Yeah, that's... Oh, no. I have it a little bit backwards. What I really want is NO2- plus H2O, which technically that H2O is not going to really show up because it's just water, but we'll include it anyway, is going to be forming with HNO2 plus OH-. So the base, so what this says is if we ever added hydrogen, it would go to the left side. If we ever added, so acid would shift the reaction right, and then if we ever added base, it would shift the reaction left. I think this makes sense to me. Yeah, okay, buffers. So 1 point is earned for the recognition that a solution produces a mixture of a weak acid and its conjugate base. I think I gave no demonstration of that. 0 points, unfortunately. So buffer is a weak acid with a conjugate base, and the net ionic equation is just the net ionic equation for that weak acid. Nothing else matters. Okay. So, part II, pirate part. The student should add 50 milliliters of the NaOH. Oh, sorry. Wait, what? Oh man, did I completely skip part D by accident? Oh man. Okay, I completely skipped CII, and I just went on to part D and wrote that as CII. So for CII, it says determine the volume in milliliters that the student should add to make a buffer solution of pH 3.4, not 3.14. So it says that they should be adding 50 milliliters for the reason that when half of the HNO2 is converted to conjugate base, then the pH will equal to pKa. That makes sense because the pKa is going to be equal to the pH with the two of these terms that are going to cancel out when they're equal, the conjugate base and the weak acid. Yes. Okay. Cool. Well, I earned no points for that because I didn't write it, but for part D, which this is actually part D, it sucks, but the buffer made by the second student is more resistant to changes in pH because it contains a higher concentration of HNO2 to react with added. I mean, I'll give myself the point, but I think it's really on the cusp. I needed to say, because she used 1.00 molar of this, which creates more weak acid and conjugate base to react with added H plus or H ions. Yeah, I needed to say include the NO2 minus conjugate base as well to be most correct. Okay. So 1 point for the correct choice and 1 point for a valid justification. I'm not going to get a valid justification. I can already tell because I'm super wrong. So 1 out of 2. Let's read their justifications. So if the HNO2 equals the concentration of the NO2 minus, then the pH is pKa. So by the way, this pKa stuff, I haven't really learned about it, but it seems like it's really important when you have a buffer, when the concentration of the conjugate base equals the concentration of the weak acid. It seems like this is important because it's when the pH equals what they call the pKa, which according to this equation, that log disappears on the bottom. So also remember that. I don't think it's going to be on my exam, so I'll still try to remember it though. So the pH of the solution would be 3.4. Since the concentration of HNO2 is greater than the concentration of this, as represented in the diagram, the solution should have a pH less than 3.4. So another way of saying this is, oh, funny, they're saying that the concentration, oh, wow. I'm just looking at their OR here. I think they might be wrong because they say the log of the concentration of NO2 minus over the concentration of HNO2. And I gotta say, the concentration here is 5/15 and 10/15, not 5/10. I really think they have this wrong. The justification is correct because it will be a fraction less than 1. So it'll be something less than 3. But it's not, yeah. I don't think this log is going to be a 5/10. I think it's going to be of 5/15 or something like that. But I can't really think about it right now. Too much going on in my head. Okay, anyway, let's move on. So now we've got the dye stuff. So it turns out that nonpolar dyes are least strongly retained by the polar paper, which means I'm literally opposite. Okay, literally opposite. So dye C is what I said, dye B is what I said, dye C. So it turns out that the nonpolar solvent is going to be attracting all of them, but I guess they're all going to move further away, and it's not going to be attracted as much. So, okay. I guess so. So for part A, I get 1 point earned for the correct choice and reference to the chromogram. I do not get that. 1 point is earned for a correct description of dye, solvent, and or dye paper interactions. So dye B moved the least, so it had the weakest. That's the exact opposite. I need to say moved the least, so it had the strongest. This is what I should have said is the strongest. Okay. 0 of 2. And dye A, I get that point. What is the valid justification? Can't be dye B. The unknown sample moves to a position that's midway between the origin and the solvent front, and so does dye A. Oh, I see. The solvent front changed somehow. That's very funny. So I only get 1 out of 2 points because I didn't get a valid justification even if I guessed correctly. The reason it doesn't go all the way to the same is that the solvent front here, for some reason, is lower, and it still is going halfway, which is the same as dye A. So, okay. Obviously, this is abysmal. That's what happens when you haven't learned about any of this stuff yet. But, yeah, I will need to know that for the exams. This is good to know. In summary, for me, what this says is when you have this nonpolar solvent and the solvent front, that the more nonpolar, the less it'll be retained by the paper, the more it'll get pushed away from the solvent, and the farther away it'll go, this dot of dye. The more polar, the less it'll move, and it is actually all defined in terms of ratios of the distance between the origin and the solvent front. Yeah, okay, that seems pretty good. And there's something called the retention factor, which is what I'm talking about, apparently. Okay, so far this is a pretty lousy performance on this exam, and I like to chalk it up to the topics that I'm not going to be tested on, but honestly, I should be strong on everything, as would be expected of a normal AP chemistry student, so I'll be continuing to work on this as I go through. Okay. So 15.2 kilojoules, we get our point here. Very nice. MCAT, MC delta T. 1 point earned for the correct amount of heat released. I got that point. 1 point earned for reporting the answer to the appropriate number of significant figures based on the experimental data. I got that point. Good for us. Good old calculations. We can do those. Okay. The final temperature measured by the second student will be less because the actual mass combusted will be less than 0.55 grams, or combustion of the contaminated sample will also require vaporization of the water in the sample. Because the student's burner contains water, it will lose mass to the evaporated H2O in addition to the combusted blah. Thus, the 0.5 not all from the so the release heat. Oh, okay, I think I earned that point. I'm saying that you're gonna not. I think that this will be. This is a better explanation. The actual mass of the blah combusted will be less than 0.55 grams. Cool. 6. So 1 point is earned for calculating the solubility of MgOH. That solubility is, so then this is the cube root over 4 because of this 2x squared over is the 4x cubed. So the solubility is going to be 1.65 times 10 to the negative fourth, which I rounded to 1.7, but whatever, I think that's fine. I get that point. And then finally I have just multiplying it by this 100 milliliters times the mass gives me 9.6, so calculating the correct mass based on the solubility. I believe I earned both those points. A welcome respite from the horrible performance of my previous questions. Okay. The SR2 plus ion is larger than the Mg2 plus ion because it has an additional occupied energy level, or shell. Coulomb's law states that the force of attraction between cation and ion is inversely proportional to the square of the distance between them. Since the distance between Mg2 plus and OH minus is shorter than the distance between strontium-2 plus and OH minus, the attractive forces in the MgOH are stronger, and therefore its lattice energy is greater. So 1 point earned for the correct comparison of cation sizes. So Coulomb's law implies that the greater distance between molecules, I'm reading my own now, in a lattice, makes for lower energy to the same charge we can ignore it. So SR is a larger atomic radius than magnesium because it has electron occupied high valence electron levels. So therefore, this will have a greater distance between lattice points. So Coulomb's law says lattice energy will be lower, and 1 point is earned for indicating that smaller interionic distances lead to greater lattice energy. Greater distance between makes lower energy. Okay, I earned both points. Again, very welcome to earn all the points on a question. Okay, 1 point for correctly combining the E values. I correctly combined, and notice that we have this 1.33, even though we're multiplying it by 2 or whatever happened back there, multiplied it by 3, that voltage doesn't change, so I get my 1 out of 1 points. I get my 1 out of 1 points. Sweet. Okay. Part I, the student should use the dichromate ion because the E value is positive, which means the reaction is thermodynamically favorable. Or just use the negative NFE thing. Okay. Cool. I earned my point. Positive E or negative G. Yeah. Bam. Okay, calculate the value of delta G in kilojoules per mole. And obviously I don't have the correct value, so I don't get that point. Pooey. But let's look at what they did. First of all, they did it the same way as us, except for having changed some stuff. So I see. Volts, I'm used to not being written as joules per coulomb, but rather coulombs per second, but whatever. I guess in chemistry you just say volt is joules per coulomb. Then this is saying coulombs per mole is the 96,485 thing. That's correct. And where does -6 come from? -6. Let's figure out where the -6 came from. I think it's going to come from how we added things. So dichromate says we have the dichromate and the hydrogen peroxide, and the moles that went into it, I suppose, are 1 mole per every 3 moles of hydrogen peroxide. That adds to 4, not 6. I'm not 100% positive what is going on here, to be honest. Unless, okay, so on the right, no, never mind. I was going to say that 3 plus 7 equals 10 minus 4 is going to equal some kind of a magical number, but it's just not. So in conclusion, I'm not really sure how they got 6, and that's something that I'm going to need to look into. Okay, let's add up my points. For this question, I got 3 out of 4. For the previous question, I got 2 out of 2 and 2 out of 2. So that gives me a 4 out of 4 for that question. I guess we're still here. For this question, I got a, oh nice, for question 5, I got a 4 out of 4 as well. And for question 6, I got just a 1 out of 4. So now let's add together all of my scores, shall we? This is going to be our little work area. So to start off, we had 2 6 out of 10s in a row, I remember, so 2 6 out of 10s. So we had, for questions 1, 2, 3, 4, 5, 6, and 7, we had 6 out of 10, 6 out of 10. Again, kind of abysmal performance. Gonna be honest. Question 3. Oh, we didn't ever add up for question 3. So I guess we got 1, 2, 3. 1, 2, 3. 3 out of 5. 3 out of 7. 4 out of 8. 5 out of 10. That is not great. 5 out of 10. So I really had room to improve a lot on these long answer questions, like a lot. I think I understand all the concepts fairly well. There are a few things I need to work on still, like buffers or dye chromatography or the electron voltage on this last question that we have the scoring guidelines on. But for the most part, I think I understand. I simply need to not make mistakes. Because if we were to go back to the first question, where am I losing my points? Hydrogen bonding. I guess hydrogen bonding doesn't happen. Oh, I flipped it around to be the opposite direction it should have been. Oh, I did my Lewis dot diagram incorrectly because I wasn't adding the 6's. Or, oh, I just should have said molecular collisions there because it literally told me to say it in terms of molecular collisions. So I think silly mistakes are the area I'm working on, or that I'll need to be working on. Okay, 4, I got 1 out of 4, and then 5, I got 4 out of 4. 6, I got 4 out of 4. So 1 out of 4, 4 out of 4, 4 out of 4, 3 out of 4. That's 1 out of 4, 4 out of 4, 4 out of 4, 3 out of 4. So pretty good performance near the end of the exam there. Let's add these guys up. They add up to 42 points. So this is going to be something over 42. What over 42? 6, 12, 17, 18, 22, 26, 29. Okay. I think what I have here is representative of how the exam could go if I'm not wary of my silly mistakes. But I also know with pretty good certainty that if I didn't make any of these silly mistakes, that I could have a score that's much closer to about 37 over 42. I only think about 5 of those points, 3 of them coming from the dye question, maybe 1 of them coming from this question, and 1 of them coming from somewhere else. I don't think I really didn't know much on this exam. It's a pure question of how well I applied my knowledge without making silly mistakes. So let's say if I've got to say one thing, it is watch the details. Watch the details. If I can do this, I think that I can turn what I know into successful answers. And the way you do that is by practicing with practice exams like this. So I'll keep practicing before the exam. I've got just over a week. And if you are also preparing for the AP Chemistry 2020 exam, I wish you luck. Whatever your circumstances, I hope that it goes absolutely great. So that's all from me. Hope you have a wonderful day. Goodbye.